if you're trying to work out, I got some videos afterwards to do some workout.
Let me know.
Do the insanity. If you master that,
We're gonna do squat challenge?
Huh?
Do non-DGX,
No. Let's learn double angles for sine and cosine. So double angles for sine and cosine are based on things that we recently learned. So let's talk about the first thing. So when you look at sine, think about this. How do you get 2 of something? What did you do to get 2 of something? You had to add them, right? You had to add them. Okay. Thank you, Alexandra, for saying that. To get 2 of something, that means you had to add 2 things together that are the same, right? So when I got this answer by adding a plus a. Right? Because a plus a will give me 2a. We agree? We're all in agreement? All right. Last week, we learned how to add with sine and cosine, aka the sum and difference identities. That's why I asked you to take out your identities chart. So when I look at sum and difference, it tells me that if I have sine a plus b, that becomes sine a times cosine b plus cosine a sine b, right? We agree? That's what we learned last week? Yeah. All right, so applying that to this, and this problem, my A would be A, and the B would also be A. A. So I plug in what I have. So I would have sine A times cosine A plus cosine A times sine A. Correct? So it's switched it around, right? So essentially it's saying that this is xy plus yx. Correct? So they're the same thing, just moved around. We agree? Because 2 times 3 is the same thing as 3 times 2. It's still going to give me the same answer. So what this can reduce to, if I have 2 things of the same thing, I put them together. So I have 2 sine A cosine A. And this is how the sine double angle identity was created. So sine 2A, take off the scarf. That is why you're hot. This dude wants to say it's hot in here with a wool scarf around his neck. Whatever, Dot. Whatever your heart tells you to do.
I'm gonna take it.
All right. So, do we understand how this identity was created?
We had a practice problem like that, right?
Kind of.
Quick question. So, how come cosine of A only stays as cosine of A?
How come cosine of A becomes cosine?
How come it's not two cosine?
Because they're together. They're one term. It's not 2 separate terms.
So you don't.
Yeah, sine A and cosine A is one term, and you have 2 of that one term.
Oh, okay, yeah.
Remember, terms are separated by addition and subtraction. Okay? So now let's do the same thing, but we're going to do it cosine 2A, which means that I start off with cosine of
A minus A.
no, still A plus A.
A plus B.
But what's the rule for this one?
A minus B.
It's minus the stack.
What he says. So it would come cosine of A, cosine of B, minus sine of A, sine of B. And in this, for this problem, A would still be A, but in the other, and B would become A. So I plug in what I have. So I have cosine of A times cosine of A minus sine of A times sine of A. When you have 2 things that are the same and you're multiplying them together, what does that become? Squared. Just like 2 times 2 is the same thing as 2 squared. So here it's going to become cosine squared A, and here it's going to become what? Sine squared A. So the first identity that comes from cosine 2A is It's not a Pythagorean yet. No. Minus sine squared A. Okay, so now that I have that one, because of Pythagorean identities, I can manipulate this to be two more things. If I first start off with substituting in for cosine squared A, the Pythagorean identity is, remember, sine squared equals 1, right? So if I wanted to substitute in for cosine A, what would I substitute in for that?
1 minus sine squared.
1 minus sine squared. So I would have 1 minus sine squared A minus sine squared A. So what would the new identity come from that one? How many sine squared A's do I have?
2.
So my second identity that I create is 1 minus 2 sine squared A. So the second identity that comes from cosine 2A is 1 minus 2 sine squared A. Okay, now this time, what if I substitute for sine squared A? What would I substitute in for that one?
1 minus cosine squared.
There we go. So here I can substitute in, I'm going to keep cosine squared A minus 1 minus cosine squared A. And I'm going to end up with cosine squared A minus 1 plus cosine squared A. How many cosine squared A's do I have?
2.
So I have 2 cosine squared A minus 1. So my third identity that comes out of this is teaching you
Like, is there a profession that uses this?
more of an engineering and computer profession. All right, so I feel like I lost some people. And I know there's not a lot of people in here, but I feel like I lost some of you. So let's go over what just happened. So what we did is that we were given a new identity, cosine 2a. And we wanted to know what would that identity be equivalent to, right? Okay, well, we used what we knew. We knew that if it's 2a, that means that it started off as a plus a. And that's what gave us the 2a. So now we're dealing with our sum and difference rules. So this is cosine of a plus b. And the rule is if I have cosine a times cosine b minus sine a times sine b, right? So that's just that identity. So we use this identity and we plugged in our variables. When we plugged in our variables, we got cosine a times cosine a minus sine a times sine a. Good? Agreed? All right, so from there we got cosine times cosine gave us cosine squared. Sine times sine gave us sine squared. So this is our first identity that we created. So we know that cosine squared minus sine squared equals cosine 2a. Okay? Because we've talked about and we know our Pythagorean identities, that means that from that identity we can create two more identities. Okay? Put the phone up, Brandy. The way we can create those two more identities is by using the Pythagorean identity. So looking at the Pythagorean identity, if I wanted to substitute in for cosine a, that means I would have to subtract sine squared from 1. So when I substitute 1 minus sine squared a in, I now have 1 minus sine squared a minus sine squared a. How many negative sine squares do I have now? 2. So now it becomes 1 minus 2 sine squared a, which created our second identity. To make our third identity, we still use the very first identity we came up with, but instead of substituting in for cosine, we're now substituting in for sine. Sine can be substituted in by subtracting cosine squared from 1. So wherever sine squared was, we plug in 1 minus cosine squared a. We plug that in, We distribute our negative because it's being subtracted, and then we combine like terms. We have one cosine A here and one cosine A here, so that made 2 cosine A's. And now we came up with our third and final double angle identities. So through those proofs, we now have these 4 identities. So we took everything that we learned before and compiled it to create these additional identities. And the reason why that was done was because someone got tired of doing these steps over and over and said, hey, there's a pattern here. Let me follow that pattern and see if I can come up with an identity. And so these 4 identities were created from someone observing a pattern. Okay? And now that we know the identities, now we can use them. Are y'all ready to use them? All right, so using the identities. Step 1 is you identify your variable. So in this problem, what would be my A? 45. So my A equals 45 degrees. So where 45 degrees is, I'm going to plug in A. So I have 2 sine of A, cosine of A. What identity does this resemble or is equal to? Sine 2A. So now I have my identity. Now I can substitute back in. And what's 2 times 45? So now I need to know what is the sine of 90. 1. On your unit circle, recall that 90 is at the top. And the coordinates for 90 is 0, 1. And my x represents my cosine, and my y represents my sine. So therefore, the sine of 90 degrees is 1. How do we feel about it? This is a basic one. How do we feel about the basic one? It's okay? All right, let's try another one. On this one, identify our variable. What's our A? 25 degrees. So I'm going to come over here. I'm going to write 1 minus 2 sine squared A. What identity is it similar to or it is equal to?
Cosine 2A.
Cosine 2A. I have my identity. Now I can plug back in my variable. And so that gives me, is cosine of 50 on our unit circle? So this is as far as we can go. How do we feel?
You should stay basic.
Okay, these are the 2 basic problems. We're going to move up another step. Okay, we're going to get just a little harder. Okay, first thing here is our variable is x. Does it really matter for us to substitute a and x in? No, but if you want to, you can write a equals x if that makes you feel better. Okay, next thing here is that notice that 6 and 3, they're common. They have a common factor, right? What's their common factor? 3. So I can make this problem a little easier for myself by factoring out that 3. When I factor out the 3, I'm now left with 2 cosine squared x minus 1. Now does this resemble an identity? So where this is, I now can substitute in for cosine. Well, I'm sorry, I should put a. Because our variable is x. So our answer is? We can't go any further. That's all we know. We don't know what x is. So got a little harder. How do we feel? Good?
What if we wouldn't change the 6 and the 2?
How do you would have done it? Okay. The other option of solving this is that if you hadn't changed the 6 and the 2, what you would have done is you would have looked at the identity that it looks most similar to. And so the identity that it looks most similar to is 2 cosine squared x minus 1 equals cosine 2x. We agree? That's the one that it looks the most similar to. So how can I make this identity look like that? How can 2 become a 6 and how can 1 become a 3? Multiply. So I would multiply this side by 3, and what I do to one side I would have to do to the. So now I know that my answer would have to be. So you either can manipulate the problem or manipulate the identity. Whichever way is easier for you to look at. You weren't even paying attention, so it's okay. It's okay. We'll address it in the morning.
You gotta take some 5-hour energy or something.
I can't. It causes me to have heart palpitations.
For real?
Yes.
You tried it before?
Yes. All right. So whichever way is easier. If it's easier for you to manipulate the problem, manipulate the problem. If it's easier for you to manipulate the identity, manipulate the identity. Okay. But the ending result is going to be the same for both. Good. All right. So let's try 6. 6. Does it look like anything we have?
No.
No, but it looks similar to something we have, right? Okay. So it looks similar to what?
Sine 2.
Okay. And this problem, it would be easier to manipulate my identity, right? So how can I make 2 sine x cosine x into 8 sine x cosine x? Multiply by what I do to one side, I have to do to the. Sorry that I didn't make that an x. So therefore, our answer is just. Because the 4 times the 2 would give me the 8. And now, what I did to one side, I had to do to the other. So therefore, my answer would just be 4 sine 2x. Or I could have done it where I said, okay, well, these problems are called double angles. So if I'm talking about double angles, then when I look at this problem and say, okay, what would make this into a 2? Divide out a 4. So this could have became 4 2 sine x cosine x. And now I would have seen instantly that my insight would become sine 2x. So it doesn't matter which way you go. You either manipulate the problem or manipulate the identity. All right. Let's start getting a little harder.
Is that changing?
Huh?
That's a theta or is that a 0?
A theta? Does it not say theta on your paper? Oh. All right, so what's our A here? 3 theta. Okay. Does this look like an identity we have? It looks like one.
Yes. Sine 2.
Huh?
Sine 2.
Yeah. Because if this was just sine A, cosine A, it would almost be sine 2A, but what's missing? So let's see. So I have sine 2A equals 2 sine A cosine A. How can I make this look like this?
Divide by 2.
I would divide by 2. What I do to one side, I have to do to the. Okay? When you are dividing by 2, that's the same thing as saying multiply by a half. Okay? So now I've manipulated my identity to fit my problem, right? So if I just have sine A cosine A, that means it can become 1/2 sine 2A. So I can bring it over here, and instead of A, I'm going to plug in what? 3 theta. So 1/2 sine 2 times 3 theta. So all I did was manipulate my identity. Once I manipulated my identity, I now have an identity that I can work with. And because I know what sine A cosine A equals, I can now use that identity and plug in my variable. Okay, I want you to try 8. Okay? All right, so again, my A is what? So when I look at this problem, I now have sine of A, cosine of A. It looks vaguely familiar to one of my identities, but it's not the exact identity. Okay? Because it's not the exact identity, then I can say, okay, which identity did y'all use? All right, so it's not quite what I need. I need to move the 2. So in order to move the 2, I get 1/2. So I have 1/2 sine 2A. So I'm going to plug in what I have. And that gave me,
Hold on, why would you have it again? Oh, because it's not what
and the sine of 30 is,
1/2.
and when you half a half, everyone gets a,
you need.
A quarter. Did anyone get it?
I got 30.
Yeah, I stopped at 30. We went right there with just.
Yeah.
Okay, so you stopped here. You didn't finish it. Is sine of 30 not on our unit circle?
No. Yeah.
It is. It's in quadrant 1, 30 degrees, right? Yeah. And it says that it's square root of 3 over 2 and 1/2. Which variable is our, which coordinate is our, not coordinate, yeah, which part of this is our, which part of this is our sine? The y. So therefore it's, so for sine of 30, I can substitute in 1/2. And 1/2 times 1/2 is a quarter. If you stopped right here, you didn't finish the problem.
So would that be half of
Was it that bad?
Nope.
Nope. All right, 9. I want y'all to take a moment and look at 9. Sine x squared minus 1. It should look familiar. Does it look familiar? Is it a double angle identity? No, it's, what is it, Don? It's a Pythagorean. The reason why I put number 9 on here is that you guys, when we learn something new, you guys get so focused on just using that something new and you forget about the old. Okay? Number 9 is something you already know. It actually comes from a Pythagorean identity. It comes from using the Pythagorean identity, right? So if this comes from using the Pythagorean identity, what's the answer?
Cosine.
Huh?
Cosine.
Good job, AJ. Okay? Reason why, I see the look on your face, Quay, is because I need sine to stay positive. So I'm going to leave sine alone. However, I need 1 to become negative, and I need cosine to move. So when I move cosine, it's going to become a, so therefore my and then my 1 is going to be moved to the other side. So I end up with sine squared x minus 1 equals. Okay? So be careful. Not every sine square now you see is going to be assumed to be a double. It either could be a double or it could be a Pythagorean. So you need to check for both possibilities. Got it? Alright. This is where last period got really, really mad at me. So I really hope you guys won't be mad at me. So the best thing for us to do is to divide the space into 3 parts. Divide here. and divide here. So now we have 3 parts.
That's a lot.
Okay? Now these type of problems used to make me feel like super smart in high school. I was like, oh yeah, this is what geniuses do. I don't feel that smart anymore. But when I was in high school, I was like, I got this. And I would actually take up a whole page deliberately. So I could just like, Mom, look, this is one whole problem. So what this tells me is it wants me to find the sine of 2 theta and the cosine of 2 theta. Well, the sine of 2 theta is equal to 2 sine theta cosine theta. And for cosine of 2 theta, we're going to use the first identity, which is cosine squared theta minus sine squared theta. So in order to work these 2 problems, I need to know what sine and cosine theta are, right? Do we know them? No, we don't. So we have to find them. Huh? She knows them? Oh, okay. All right, so we're going to find them based on what's given to us. Well, they gave us tan theta. They were so kind to give us tan theta. So when we look at tan theta, it says that tan theta is what? -3. Is there an equation that we can use with tan theta in order to find, in order to find something related to or something that is sine and cosine? Okay, ratio will be cotangent. How about a Pythagorean?
Yes.
What if I had 1 plus tan squared theta equals secant squared theta? Is that not a Pythagorean identity that's on your chart that you should have out in front of your face?
Yes. So does that mean the secant squared theta is -2?
No.
Sure.
I'm positive because you have to square them. All right, so let's plug in what we know. So we have our identity. So let's get to solving. So I have 1 plus -3 squared equals secant squared theta. And what do I get from here? What's 9 plus 1?
10.
So I have now 10 equals secant squared theta. How do you unsquare something? So the square root of 10 equals secant theta. Well, I don't need secant theta. Who do I need?
You need sine.
I need cosine. Can secant theta lead to cosine? It's the what? It's the reciprocal of cosine. So if it's the reciprocal means I'm doing what with my value, my number? Flipping it. So instead of square root of 10, it's going to become, is there any point of writing square root of 1? Who writes the square root of 1? Who does that? Huh? All right, so I have this. The problem here is, are you allowed to have a radical in the denominator?
No.
No. Way back, in algebra, you learned that you're not allowed to have a radical in the denominator. How do you get rid of a radical in the denominator? How do I ratify it? Good job, AJ. So therefore, the cosine of theta actually equals all right, so I found cosine. Now what do I have to find? All right, how can I find sine? Is there another Pythagorean that I could use?
Yes.
There is another Pythagorean that I could use.
Yes.
What's the other Pythagorean I can use?
1 plus tangent. 1 plus cotangent.
Is that not is this what we were doing last week? We were using this identity. If we knew sine or cosine, we could use this Pythagorean identity to solve for the other one that we didn't know. So in this case, we know which one. We now know cosine. What's cosine again? Let's check. Square root of 10 over 10. So I can plug in. So now I have sine squared theta plus square root of 10 over 10 squared equals 1.
Well, you see, what you're
Oh, I know this one.
split the 10 on the other side.
Okay, so how do I move a positive 10 over 100? I'm adding. What's the opposite of addition? Subtraction. So you're going to go away, and you're going to come
Oh, this is like that one.
that we did last week, like she said just 2 minutes ago. I know.
I heard you.
All right, what's 1 minus 10 over 100?
90 over 10.
90 over.
What kind of 90? Positive? Yes. Is it done?
No.
What do I have to do?
That's clear. You have to
I'm going to reduce it before I do
reduce it.
anything.
That's 9 over 10.
And that's going to give me 3, 9 over 10?
9 over 10.
All right, that makes it a little funner to. Now,
You square root.
square root, square root, square root. So sine theta equals?
3 over.
Sine theta equals 3 over square root.
Oh no, we have a
We have
problem.
another radical in here.
I have another radical in the denominator, so what do I have to do?
Ratify.
Ratify. All right, let's glance at all of our hard work. Zoom in. How do we feel? It's a bit tedious, but it really isn't.
I didn't know there was a good team.
We're not done, are we?
No, we haven't even answered the question. Yes, Anna, we're going to plug in for cosine and sine it to answer the question. But before we do that, what I want you to notice is it gave us a restriction. It told us that our angle only lies in quadrant 2 and in quadrant 3. The reason why I know this is because it says between 90 degrees and 270 degrees. If our angle lies in 2 and 3, what does it tell us about our cosine?
It's negative.
It's negative.
Our cosine is not actually a positive square root of 10 over 10. It's actually
Negative
a
square root of 10.
negative. So let's go ahead and add our negative there. Because that's what this is your restriction. All right, so we did our restriction. We have our cosine. We have our sine. So can we answer our question now?
Yes.
What is the sine of 2 theta and cosine 2 theta? Can I zoom back in?
Yep.
Let's solve. So A is sine of 2 theta. So I'm going to plug in what?
3.
What's sine?
3 times 18, 19.
Okay. What's cosine?
So what's the... Oh.
Okay. So we plug those in, and now we just got to multiply and simplify. Okay. What's 2 times 3? 6 times negative 1 is?
Negative 6.
Okay. Square root of 10 times square root of 10 is?
1 over 10.
10. When you take a square root of the same value and square it together, you get that it sets itself free. Because the square root of 100 is 10. And what's 10 times 10? So I'm left with negative 60 over 100, which reduces to what kind of 3 over 5? Whoops. You did So once you have the values, the plugging in is the easiest part. We just got to get to the plugging in. So now you got to do B, the cosine of 2a. All right, so in this one, I'm now doing what? All right, so cosine squared theta. So negative square root of 10 over 10 squared minus 3 square root of 10 over 10 squared. Those are our sine and cosines, right? What happens when you square root?
Cancels out.
It sets itself free. So you get negative 10, and what's 10 squared?
Dang it.
Oh, this is a positive. A negative times a negative is a.
I didn't know we had to.
So what's 10 minus 90? Negative 80. And what does that give us? There are your two answers. Alright guys, on your homework, the odd problems are extra credit, the even are the actual homework assignment. Your homework can be turned in tomorrow or you can turn it in on Monday.
Are you saying to Ace today?
I will be at school till about 4:45 today.
You know I need one time. You know I'm into like 5.
That's all I got today. Huh? Oh no, I'm leaving today. I have to leave today at 5:45. At 4:45. Look, darn, you're trying to make me say the wrong time.
Dang.
All right.
It is fixed. It is fixed. I don't even have it there.